We are doing our final section that will be covered on the unit test, so 11.7 on ratios of areas. There is an 11.8 on probability, but we will not be covering that this year. So we are stopping from 11.1 to 11.7, and that is what will be on your unit test. So next week, after this lesson today, next week we will review. You'll have an entire period to review and ask your teacher questions. And then the following lesson after that, we will have a test. So 11.7 is on ratios of areas. So we are going to be comparing different ratios, so comparing areas of triangles to each other or comparing lengths of sides to the actual area that it produces. So we'll be looking at some ratios here. So this first question says, if 8 ounces of dough are needed to make a 10-inch pizza, how much dough will be needed to make a 20-inch pizza? Okay, so first of all, just think of that big pile of dough that you see when you go to a pizzeria. What do they do with that dough? They usually smush it out onto a wooden or something, some kind of table. It may not be wooden. And then they toss it up in the air and they try to make it a circle. That's what they're making. Now, you might say to yourself, well, ounces of dough is three-dimensional, so why aren't we talking about the volume? Well, we're taking out, because they're the same thickness, we're taking that dimension out. So really, we're just going to look at the diameter of the pizza as compared to the area of the pizza. So remember, when you're ordering a pizza, and if it's 10 inches, 12 inches, 16 inches, that is the diameter of the pizza. So here, my diameter is 10 inches. So if I'm going to find the area, well, let's recall the area formula. That's pi r squared. So the area of a 10-inch pizza is pi times 5 squared. So it's 25 pi inches squared. For a 20-inch pizza, again, the diameter is 20, therefore my radius is 10. So the area equals pi times 10 squared, which was 100 pi. So that is 100 pi inches squared. Part C says, find the ratio of the area of the small pizza to the area of the large pizza. Okay, the small pizza, we said the area of the small pizza is 25 pi inches squared, and the area of the large pizza is 100 pi inches squared. So what is that ratio if we were to simplify? Well, 25 goes into 100 4 times, and my pi's cancel each other out, right? If I did that as a fraction, 25 pi over 100 pi, the pi's cancel each other out. 25 goes into 100 4 times, so it's 1/4, or a 1:4 ratio. So it says, based on this ratio, how much dough would be needed to make the 20-inch pizza? Okay, well, we said 8 ounces of dough were needed to make a 10-inch pizza. So how many ounces of dough were needed to make a 20-inch pizza? Okay, you can't set it up like this because that's not the relationship. The relationship isn't double here, but it's a 1:4 relationship. So therefore, this needs to be 1, and we're going to need 4 times as much dough, right? So if we needed 8 ounces for the 10-inch pizza, then we're going to need 4 times that, or 32 ounces, to make a pizza that has twice the diameter. So the radius relationship was a 1:2 relationship, right? That was your radius to your radius, but your area relationship was a 1:4 relationship. And because my dough we're spreading that out into an area, we're going to have to quadruple or multiply it by 4 times in order to get our final answer. We'll do some more of those on the back of this sheet if you didn't understand that. Okay, the next thing we're going to look at is relationships in our triangles. It says, find the ratios of the area of each set of triangles. So what I want you to do right now, this will be good review and practice for you, is I want you to pause the video and I want you to fill out all these blanks right here. So I want you to find all of these areas, and if you want to go ahead and move on and find the ratios of those areas, that's fine. And then I will review it with you, and all my work will be up there, so we'll just review the ratios. So pause and calculate all those areas. Okay, so hopefully for section A, you got the area for triangle ABD to be 8 units and the area for triangle CBD to be 12 units. So now let's do the ratio of those two things. So that's comparing 8 to 12. So if I'm reducing 8 divided by 12, right, they're both divisible by 4, so that becomes a 2 to 3 relationship. 2 to 3 relationship. Okay, how does that relate to the dimensions over here that were originally given? So here on the first triangle, my red one, the base was 4 units big. And on my second triangle where I wrote in blue over here, the base was 6 units. So if we compared those bases, that would be 4 to 6, which actually reduces to 2 to 3. If we compare their areas, when they had the same height, so they have equal heights, if we compare their areas, that also simplifies to a 2 to 3 relationship. So if we look down here at this first sentence, it says comparing areas of triangles. If two triangles have equal heights, then the ratio of their areas equals the ratio of their, well, look at that. They had equal heights of 4. The ratios of their areas, 2 to 3, were equal to the ratio of their what? What's the red and the blue represent? That represents the bases. So the ratio of their areas equals the ratio of their bases. Okay, let's look at number 2. If we're going to do the ratio here, we're going to do the ratio of ABC to ADC, so that's a 2 to 1 ratio when I simplify. Okay, well they share the same base, so we're not going to compare that, but if we compare their heights, well the big one is 4, the small one is 2, and I did big area to small area. Once again, what happens when I reduce that? I get the same relationship here. So if two triangles have equal bases, then if two triangles have equal bases, then the ratio of their areas equals the ratio this time of their heights, right? How do we get the same ratio of there? We compared height to height, and that ended up being the same ratio. For letter C, similar triangles. So this says if two triangles are similar, then the ratio of their areas equals, okay, let's look at their ratio of their areas. So ABC, the small area compared to the large area, that reduces to 1 to 4. 9 goes into itself 1 time, 36 goes into itself 4 times, so it's a 1 to 4 relationship. Okay, so if they're similar, then if we compare their dimensions, length or bases to base, that's 6 is to 12. Well, if we reduce that, that's a 1 to 2 relationship. And if we compare 3 is to 6, that's a 1 to 2 relationship. So how do these relate to each other? It says if two triangles are similar, that's these two here, then the ratio of their areas, that's this one, equals the blank of their scale factor. Here's the scale factor, 1 to 2. How do you go from 1 to 2 to 1 to 4? Maybe that's tricky for some of you. But it's the square. You have to square 1. So 1 squared equals 1, and 2 squared equals 4. So you take this scale factor, you square each dimension, 1 squared, 2 squared. You square the scale factor, I should say. And that is the relationship of their areas. Now notice, this does not have a little theorem written beside it. It's not a theorem. This does not appear on the theorem sheet, which means you need to remember it because yes, it still might be assessed. It will be assessed actually, not might be, it will be assessed, but it will not be on your theorem sheet. So you need to remember these 3 things. If two triangles have equal heights, then the ratio of their areas is equal to the ratio of their bases. If they have equal bases, then the ratios of their areas is equal to the ratio of their heights. If they are similar, then the ratio of their areas is the square of their scale factors. Okay, let's move on to the theorem that will be on your test. This is a theorem. I did not write that, but this is a theorem right here, and it will be on your test. Okay, so again, I want you to pause. I want you to go through this sketch, do this, calculate all these things, see if you can come up with this relationship down here for the theorem. If you cannot, then you can watch the video and you can listen to me explain it. But I'm going to go through all these steps as well. Maybe what we can do, well, yeah, I already give you the dimensions, so we're all going to have the same stuff. So go ahead, pause, and do these steps and see how you do. So you should have calculated the area of the 3 by 5. Well, that's just 3 times 5 is just 15. The area of the 9 by 15 was 135. It says find the ratio of the small rectangle to the area of the large rectangle. So we did small area to large area, which reduces to a 1 to 9 relationship. It says how does the area ratio compare to the ratio of the original side lengths? Well, a 3 to 9 relationship reduces to a 1 to 3 relationship. So the side lengths had a 1 to 3 relationship, the areas were 1 to 9 relationship. So what am I doing to my 1 and my 3 to get from here to here? Okay, think about that. Then it says calculate the perimeter. The perimeter of the small one was 16, perimeter of the large one was 48. The relationship between the perimeters, small to large, was a 1 to 3 relationship. Okay, how does the perimeter ratio compare to the ratio of the original sides? Well, the perimeter ratio is the same as the original side ratio, and the area ratio, I'm hoping you are saying, is the square of those. So the theorem says if the scale factor of two similar figures is a to b, then the ratio of the perimeters is that same scale factor of a to b. We don't do anything. 1 to 3 stayed 1 to 3. However, our areas, because they're two-dimensional, that's going to change the length and the width dimension, right? They're both increasing by 3. This is 3 times 3, 5 times 3, which is increasing an area of 9 times more, not just 3 times, because it's two-dimensional. So therefore, your area relationship, if it's a to b, is a squared to b squared. So a being 1, 1 squared is 1, b being 3, 3 squared is 9. Okay, now once again you should pause and try some of these problems on your own. Apply that theorem above and see how you do. And then you can unpause and see the answers, listen to the answers if you need to. Okay, you should have gotten 1a to be 3 to 5. If they're similar triangles, then yes indeed, and they have a relationship of 3 to 5, then you're going to have a corresponding sides is a 3 to 5 relationship, corresponding perimeters, or sorry, the perimeters will be a 3 to 5 relationship, and in the areas you'll square those. So the key words here that I'm not sure I quite emphasized is similar. If the scale factor of two similar figures. I said that because when I started to answer the true-false questions down here at the bottom, this letter C kind of threw me for a loop, and that is false. And you might have gone through and said true, 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 true. But letter C is false. Why? Well, it's missing the word similar. Okay, well, you might say to yourself, well, letter D doesn't have the word similar. Letter B doesn't have the word similar. That's true. But letter B says if the ratio of the areas of two equilateral triangles. It's impossible for equilateral triangles to be anything but similar to each other. So by using the words equilateral triangle, we're assuming that they are equal, or that they're similar. We know they're similar. Here it's squares. Squares are all similar to each other. But if you look at this one, if the ratio of perimeters of two rectangles is 4 to 7, so here's perimeter is 8, perimeter is 14, that's a relationship of 4 to 7. Will their areas be, the ratio of their areas will be 16 to 49? No, the area here is 3, the area here is 10, 5 times 2 is 10. That is not a square scenario because these are not similar figures to begin with. So this relationship up here in the theorem only works for similar polygons, for similar figures. Okay, A, B, and D were true. C was false because it lacked the word similar. There's your answers to 1. If you have more questions, make sure you ask your teacher. Review sessions next week during lunch if you need them. See you soon. Have a good